You have the PSLV in India that we used a few times for satellites from TU Berlin, and then you have launchers like the Ariane in Europe, which is quite big, and then you have the Soyuz. Nowadays, there are satellites that are rockets that are built to transport 100 kg to the orbit. In several countries, there are new developments like that. So faster launch into orbit, cheaper prices, lower prices for getting satellites into orbit. So there's a big trend towards that. So the total small satellites launched here in numbers, it keeps increasing. Small satellites under 600 kg is what this graph is showing. And then you see the yellow line is communication as percentage of small sats. Communication is one area that is increasingly attractive now. Maybe some of you already have an idea of what missions are responsible for that part, what type of application we're talking about here. We'll get to that later. And then this is maybe almost shocking, the number of proposed systems of satellite constellations, or number of satellites as part of proposed satellite constellations. Here you can see the proposed constellations, like how many companies announced that, or companies announced that that they want to send a constellation up there for Earth observation or low Earth observation communications, or low Earth orbit communication, for machine-to-machine communication, and for other observation applications with medium resolution radar, etc. So you see the number of constellations. This is already a lot. But if you see the number expressed as satellites alone for low Earth orbit communication, you see 68,000 satellites. So nowadays we have 3,000 plus satellites in orbit. Soon we're going to have tens of thousands of satellites in orbit. So you can, of course, not all of these announcements will become reality later. I'm absolutely sure about that. But some will go away, and then there will be new announcements. So the trend will definitely continue, and we're going to be faced with interesting problems as engineers, being more responsible with the use of space. So here are some examples of mega constellations. So I'm sure you're familiar with some of the names here. Boeing is working on internet. OneWeb constellation from Airbus is working on internet. Starlink, SpaceX, Elon Musk wants to provide internet. Even Amazon wants to provide internet. So this is the one big communication application that is gaining popularity right now. Internet through space. I mean, if you think about it, it makes sense. I mean, most areas on this planet are not covered with an internet connection. And if you have a satellite internet connection, it's very rudimentary. The services offered here with those constellations are, you can really do something. You can even stream content. So everyone on this planet will have access to the internet at some point. So this is really interesting. You can maybe get a feeling for the market potential of something like that. And then, of course, yeah, there are interesting constellations like from Planet Labs, or now called Planet, for Earth imaging. So Planet has the Flock constellation with small CubeSats, and they take a picture of the Earth once a day. So a complete picture of the Earth once a day. And just imagine you have that database, the picture of Earth once a day for all days, and then you can scroll back and go back and predict the future, and you can do a lot with that. And it's not just pictures, visible pictures like you find on Google Earth, but you can also find different types of images. So this is, for example, the Starlink constellation, or the one satellite from the Starlink constellation, just to give you a feeling. It's 227 kg, and is in an orbit in 550 kilometers. So there will be several thousand of those satellites in space, and they're interconnected, basically connected to each other, and can exchange data and provide internet. Then this is one of the Dove satellites. So they have several versions, though. And then most of the satellite is used for the payload. Here you can see the camera. And this is quite a small satellite. So this is a 3-unit CubeSat with deployable solar panels, and then here's an X-band antenna. And then you can already see this is, of course, this is not the highest resolution picture. So, but you can do a lot with that. Here you can very well imagine that, okay, in agriculture, this is going to be really useful, and for many other applications too. So I want to mention another thing here, because I know that there are many students in this audience, or at least I assume so. It's that there are several career paths to the space sector. So if you kind of get excited for this topic, and you think, oh wow, this is not only exciting, but there's a lot of potential for me as an engineer or whatever you do, why not have a jump at it and try it out. So there's a demographic curve here, and you see that many people will retire soon, or are retiring at the moment. So the industry, the space industry, is always looking for people. I'm managing a space engineering master's program at TU Berlin, and we know from our graduates, they land in the European space industry. Most of them work in Germany in several companies, small startups, big companies, the German Aerospace Center, the German Space Agency, Germany Space Agency. And there's a big demand, not just for space engineers, but also for other engineers, and I will talk about that too. So there's some career options for this for joining the space industry. So of course you can be a space engineer. So your main role is, or the main idea behind it is, when you study space engineering, is that you become a systems engineer, meaning that you have a good broad knowledge of all the topics of space engineering, meaning how to operate a spacecraft, how to build one, and you're a good communicator, and you've done several projects, curricular projects, extracurricular projects, and you know the experience of getting a space system from an idea into space. So you're a key player who's able to talk to all other discipline engineers. With discipline engineers, I mean things like mechanical engineers, electrical, software, communication engineers. Those are people who have a certain discipline, but may not be able to see the bigger picture from their perspective. So this is one of the main goals of space engineers. But of course, you only need a limited number of systems engineers. And if you're a space engineer, of course, you can also develop other subsystems. So you don't necessarily have to be a systems engineer, but you can also join the industry as one of the discipline engineers. Of course, there will be people who design very complex electrical circuits. This is normally not done by space engineers unless they have special interest towards that and some education. But you have lots of electrical engineers or software engineers that develop the software for satellites and the ground infrastructure, etc. So then you can also join as a technician and support or do assembly integration or take part in testing. You can join as a scientist, as an astronomer, atmospheric scientist, physicist. There are many positions for that too. And or as a data analyst, that's also an option, or you can even join the administration. So there are many different types of positions in the space industry. I just want to encourage you to take a look at it, and maybe you'll find an interesting path. Just to give you an idea of space systems engineers in Germany and Airbus Defense in Space, roughly estimated numbers are 12,000 employees in the space sector, or 12,000 employees, half of them work in the space sector, 50% are engineers, and 10% are systems engineers. Then the German Aerospace Center, DLR, which is basically the space agency, has less systems engineers, because they do more research, so they don't have the big satellites that they integrate, like companies like Airbus or one of the biggest manufacturers, OHB, in Germany. So 5 to 10% are space systems engineers, so key players that have a connection to all engineers, management, etc., that lead satellite projects. But as you can see, then the remaining part, the 90%, need to be other types of engineers. So if you do some little continuing education in the space sector, do some extra courses, or just start interning in a space company, then there are good chances that you can land there. So just a few words about what's done at the Chair of Space Technology at TU Berlin. So this is the rooftop with the ground station and the antennas. So roughly 50, 60 researchers work at TU Berlin on different satellite projects, rover projects, and additive manufacturing for in space, etc. So different types of projects. So there's of course education, research, and what we aim for always is to give our students an hands-on education. So our students always are involved in projects where they build rovers, autonomous rovers, take part in different student competitions and campaigns. They build small satellites or subsystems of satellites and test them. They can build rovers and propulsion systems, rockets, propulsion systems. So this learning by doing and failing and trying again is something that is really important for space systems engineers, because experience is one of the key elements of becoming one. TU Berlin has launched many satellites. I think is one of maybe the first leading, or the second place maybe, university with the most satellites in orbit. So nowadays it's even, I think, 27, and there are a few more in the pipeline. And the satellites are doing different things. So TU Berlin builds miniaturized systems, constellations, builds new equipment, like innovative equipment for attitude control, for example. So the satellites are in the range, nowadays in the range of like 1 to 20 kilograms. Or we even have constellations that are just 330 grams per satellite. So it's even getting smaller. And yeah, I mean, just imagine you have your smartphone in space, just an enhanced version of your smartphone in space. That's pretty much what we're able to do now at TU Berlin. And the satellites serve different purposes. So we have, in the beginning, of course, we had technology demonstration, making it possible to send a satellite into space that is so small and has like a failure tolerant system, meaning with redundancy, and it's quite complex actually. But we have applications like communication, where we have constellations where that test concepts like potentially increasing the throughput when you talk about communication or internet in space. We have satellites that like monitor the usage of frequencies in space. Just imagine thousands of satellites in space communicating the whole time. And when you sit in your car, or when you sit in some car, you can scroll through different radio stations and get the radio station. And if the bands are too close together, then you might have a problem identifying one station clearly. And the same problem you'll have in space when you have lots of satellites up there. So the frequencies need to be coordinated very well. And we have, for example, a mission that observes the usage of those frequencies so that this can be optimized. We have lots of Earth observation satellites that, for example, are tailored to detect forest fires. So forest fires are always a topic in several countries, especially this year. It was quite extreme in many parts of the world. And the satellite helps to detect and map forest fires. So lots of different applications. Lots of different satellites that we have. This is the CubeSat series, 1-unit CubeSats. They're quite sophisticated. So they have 3-axis attitude control. They can automatically control themselves, their attitude in space. And here you can see some pictures of the small CubeSats. And for this size is actually quite quite impressive what they can deliver. Our slightly bigger satellites deliver much crisper, clearer pictures. It's not an extremely high resolution in this picture at the moment, but you can see that it is crispy clear. So for forest fire detection, etc., you can do a lot with that already. Of course, we have ground stations, mission control rooms, integration facilities, etc., just to give you an idea where we come from, basically, what our expertise is, and just to give you the idea that we're also humans, and we there's not only the hard part of engineering and the working, although many students, of course, work on many things a lot in the labs at night, but there's also the fun part. We have a very international environment with students from all around the globe, and many students from India, by the way. So then, yeah, thank you very much for your attention. So if you have any questions, then be happy to answer them. Yeah, so I don't know if questions are asked by the audience, or if there will be some questions in the chat, or if we just give people a longer break. That's also okay.
Yeah, Ken, it was a very wonderful experience. Now our offline audience want to ask you the few questions. They have some queries.
Okay.
So I'm inviting them on the dais. Yeah, please come. They will join on my place for asking one or two questions.
Wonderful.
Yeah.
Very hearty good evening to you.
Good evening.
So, as my question was this, that you have explained so much good about the small satellites and the establishment of it. So, do you think about the cyber security of these all things? Because as for the raising concern, the cyber war and the cruciality about the satellites hacking, as the NASA is using OICP for that, for the security of the system. So, do you think that pen testers are also giving opportunity in this field for the defense services of your satellites because of network jamming in the crucial areas where you can use the networks for the GPS system and location? So do you, what's the point of concern is that basically do pen testers are also very of significance for satellite security? Do you really think there's a job endorsement for pen tester in satellite industry as a cyber tech?
Okay, so I'm not sure about the term. That was a very good question. What did you say, pen testers? What was the term?
Actually, I was asking, do the cybersecurity pen testers have an presence for the cybersecurity of the satellites, because there's a significance of cyber wars in every aspect in the industry.
Yeah. Okay, so I understand the question. So you're saying someone from a background in cyber, security, what are the opportunities in that sector? Is the sector thinking about that topic? So from my perspective, from my academic point of view, of course we think less about it because our satellites are not so capable as of doing any damage or harm. The small satellites that we built don't even have a propulsion system, so that they couldn't even do things like attack other satellites, and the data that they provide is not that interesting for potentially for misuse. But constellations, bigger constellations that provide internet services, like if you think of Starlink, of course, just imagine you have millions of subscribers and someone hacks your satellite system. That's going to put a lot of pressure on them. So yes, there are definitely opportunities for people that work on security. I've heard of interesting concepts like, how about cryptocurrencies generated from space, like have satellites do the mining. So you have all sorts of interesting concepts that come to my table, and those topics will be more interesting. Yeah, in the defense sector, I haven't worked in the defense sector, so satellites that are used for military purposes, yes, I'm sure they have divisions where people talk about security. In the industry medium, and in academics not so much yet.
The main point of concern was that because as you are in this profession for the satellite industry, you also know sometimes the sensitive data is encrypted in it, and that is some key to resource of. That's why I asked, because some of the professional hackers you have heard about Anonymous Crew, the Zuzu hackers. These are the professional ones. They can crack anything. There's no like any foundations for them. So as far the cyber industry is also into satellite also, as satellite industry is also containing some sort of sensitive information that has been transmitted to one part to another part of the world. So for
Yeah.
that, I was asking, like, as a pen tester, there's also, like, I guess so there should be, industry should provide a lot number of jobs to the pen testers, because there's also need of cyber security in satellite industry. For cloud computing we are having, for normal work of usage we are also having, for personal privacy concerns we have cyber security. So
Yeah.
that was the main concern. So it was a good time. Thank you for giving a valuable time to us.
Okay. Thank you very much for your question.
Hi, sir.
Hello.
So basically, we wanted to ask that how we can expand the network of internet in India, as Starlink is coming to India with the satellite internet systems. And I was also thinking about the possibilities and increments in the cases of satellites as a server system.
Yes, sir. Since technology is going very fastly, and we think that we can connect satellites with the server system. And what are your
Or we
views
can
about
make
it?
a network or node of systems, server systems, that can
Decentralized
work in the
also.
space so that the data can be
Mhm.
transferred
Okay. So
possibly.
this is nice to see some fresh ideas. Um, you mean the servers are in space, or the satellites connect to servers
Yeah.
on ground?
Server systems as well as systems.
Server systems as satellites.
Yeah.
Like if we can prepare a Raspberry Pi node for the satellites and then we can run them.
Hmm. Okay. So what problem do you want to solve with that?
Uh,
So, is there a way to connect satellites and make them a server system rather than storing tons of data on the servers? We can directly connect them to the satellites. So, how can we do that?
and as we see that AWS and everyone is doing the server systems, but
They are centralized.
they are centralized. But the thing is that it is increasing the carbon footprint and everything is increasing, and energy is also increased. So in the space, we will be using solar energy to power the satellites. So is it feasible to do that?
I mean, it's definitely feasible to do it. Yes, you can set up servers of all sizes in a satellite and connect it to ground. You can have a distributed satellite system with servers. Just imagine, yes, you have that. It's possible to build it from the engineering perspective. The bigger question you want to ask yourself is what problem are you solving? Like, who has a problem? Who would come to you and say, I need servers in space because it's more secure or it's whatever. So otherwise you can't find a customer. So sometimes you have great ideas from the technical part of a point of view, like we want to build a cool system or think we see all those possibilities of doing something, but then we're looking for a problem for the solution. So we found a solution for something, but we don't have the problem that we need to fix for that solution. So that would be my advice here. Technically, it's possible. It's great. Yeah, I don't know. Nothing comes to my mind at the moment, but it doesn't mean that there are applications maybe in the future.
And how can we connect with you? Do you have a mail ID that you can share so that we can contact you
Yeah.
for the discussions?
Just a second. I mean, you can. I don't know if you when you use LinkedIn, you can just connect with me through LinkedIn. I can also share my
Yes,
email
we can
address.
send the connection.
Since you're interested in business, I just recently uploaded something on YouTube regarding business for students, especially because what you just asked me, I get that question maybe once a week for different types of ideas from students. Email address, which is my No text. Everything. Or here. You can just use YouTube. Live in Berlin. .de. As you wish, you can just use LinkedIn, email address here, or any other way.
Okay, sir.
Thank you, sir.
Thank you, sir.
Of course, yeah. Thank you for your question. Oh, I can't hear you for some reason. You were audible, but I think maybe you're on mute right now. No, not yet. I think it still shows the mute symbol. The muted symbol. Now it's good.
Anyone in the online mode, if having any query, they may ask or raise the hand. Anyone in the online mode having any question, raise your hand.
Okay.
So yes, Cam, it was a very fun. Yeah, someone raised the hand. Yes, Tomar, please ask your question. Yes, please ask your question.
Sir, can you hear me?
Yes.
Yes.
I wanted to ask about the problem if the number of satellites are increasing in the sky. How will the problem of like the satellite disturbing the astrophotography will be tackled?
The astronomy. How it will. Your question is how it. Okay, so this will, yeah, very good. This will affect astronomy because
Astrophotography, sir.
astrophotography, yes. Because like when you take pictures as an astrophotographer, you have you need a lot of time. You need seconds
Yes, sir.
to take that picture, right? So the problem is satellite travels around Earth around 90 minutes. That's really fast. That's and so you have potentially lots of satellites that travel around Earth and that will cross that picture while you wait there for a few seconds. And then you have that that line of that satellite, white line.
Yes.
I'm just checking.
Yes, the main problem is the brightness that the light reflected by the satellite.
Yes. Yes, exactly. So I'm just checking if I see a picture. Yeah. I just give me a second. I can share a picture like that.
And sir, this problem is increasing with the rise in the Starlink satellites.
Exactly. Yeah. With lots of satellite constellations.
Yes,
Here
sir.
you can see that. Take a picture. You see that line here, and it's going to be problematic in the future for astrophotographers. But there's not the only problem. There will be different problems with increasing numbers of satellites.
So, like, how this problem is being tackled right now? Any idea?
That's where you come into play. So, as engineers, there are several types of potential solutions. We try to bring back our satellites within 25 years, meaning that we don't select a too high orbit, so our satellites burn in the atmosphere after a while. There are systems that are being developed for removing satellites from space. either a satellite catches the other satellite and removes it, or each satellite has, I don't know, a drag mechanism on board, a really large balloon or sail, and then from the drag, the satellite comes back down to Earth faster, or you can use a propulsion system with additional propellant to come back down faster. So we try to reduce satellites from space, but this is like a very complicated topic and not is only in the research phase right now. So there are no solutions yet, but there will have to be solutions for this problem.
Okay, sir. Thank you.
Okay, thank you very much. Yeah, it was a pleasure. To be with you today.
Sir, I'll be connecting you on the
Yeah, please do that. Go ahead.
Okay.
And thank you very much for the
Yes,
invitation.
anyone else?
Well, even have to head back to another meeting in 4 minutes. So if it's okay, then you can excuse me.
Yeah. So yes, Kim, it was a very wonderful experience by listening you. I'm sure that next time probably we are able to greet you at our campus. I hope that the COVID situation will improve and will greet you in person to at our campus. You
Wonderful.
have given very wonderful information about the big world of small satellites, just naming by the companies and country-wise. You have also mentioned about the categories of the satellite, mentioning about the either it's going to be used for internet or for the image or something else. You have very wonderful explained about the career path in space sector. You have elaborate about the space technology, having the category of the miniaturized space, distributed space, and application of space system. You also explain about the component of the small satellite. You also informed about the B-Set Cube series. And lastly, wonderful experience with the TU Berlin about the campus, about the admission, about the Indian student. It was a very wonderful experience with you. So yes, I thanks for all your speech and the discussion, and I have hopes that our online, offline, all the students have enjoyed the session. As the token of appreciation, yeah, we just want to offer a e-greeting or e-certificate to you. Please accept my colleague is going to offer you. Thank you.
Wonderful. Thanks a lot.
Yeah.
Oh, thank you. Wonderful. That sounds good. Yeah, it was a pleasure. So thank you very much. Yeah, and then I wish you all a great conference. Thank you very much again for the invitation. You've also been a wonderful audience. Great questions. I see many motivated students in the audience, and yeah, always be happy to join again. Then I wish you a great conference. Have a great day. Then hopefully see you soon.
Thank you, Cam. Thank you, and have a good day.
Bye bye.
Bye. Take care. Now we have a 10 minutes break as participants. We will meet again here for the next keynote after 10 minutes. Hello, Melina. Dr. Melina, are you there?
Yes, I'm here. Yes, I'm here. Hi.
Yeah.
Hello.
Yeah. So, hi. How are you?
Yes, I'm well. Yes, I'm listening to the previous talk.
Okay, great. So, Dr. Melina, we will start in next 10 minutes. We have a 10-minute break. So, if you want to test your presentation, you can do right now.
Yes, thank you very much. Yes,
okay.
thank you very much.
So, please share it. Yeah, it is visible. Kindly make it in presentation mode. Yeah, it's fine. It's fine. So any audio is there inside this presentation?
No, it's just
Okay.
the text.
Okay, no issue. Okay, great. So we'll start in next 10 minutes.
Okay,
Okay.
that's fine.
Okay. You can stop sharing. Welcome back. Now we are starting with keynote 4 of day 1. We have with us Dr. Melina from United Kingdom. To welcome Dr. Melina, I request Dr. Sandeep Joshi sir to proceed the event. Dr. Melina, are you there here?
Yes, I am. I'll just share.
Okay, fine. Yeah, please.
Yes. Well, welcome everyone. And thank you very much for the invitation.
Yeah, good afternoon, Dr. Milena. I'm Dr. Sandeep Joshi from Conference Site, General Chair.
Yes, very nice to see you kind of in person like this, by the video link. Thank you very much.
Yeah, Dr. Milena, I'm just going to introduce you in front of my offline audience as well as the online. So I'm going to read out about Dr. Milena. Dr. Milena obtained her diploma degree in electronics and electrical engineering from the University of NIS, Serbia, and the PhD degree in computer science from the University of Nottingham, UK. Her main research interests span area of intelligent mobile and disconnection tolerant networking, complex temporal graphs, self-organized security, and distributed predictive analytics with application to autonomous vehicles, mobile social networks, mobile clouds, smart manufacturing, and telemetry. She has been awarded multiple EPSRS and EU grant for my research and published over 80 papers in premier conference and journal venues such as Elsewhere, Ad hoc Network, IEEE Transaction of Industrial Informatics, IEEE Transaction of Vehicular Technology, IEEE Transaction of Parallel and Distributed System, IEEE Multimedia and ACA Multimedia. She was among the first people in Europe to start working on disruption and delay tolerant networks and have a research project funded. She is interested in a number of open research questions such as improving energy efficiency, designing new and more efficient data dimension and routing protocols, and new adaptive security and privacy techniques for data transmission in challenging environment. So thank you, Dr. Milena. Now we invite you to share your slide and start your presentation. We welcome you, madam.
Thank you very much for this introduction. Can you see my slides? Yes. Yes.
Yes, we can. Yeah, it is. We can see now.
Okay, that's very good. Thank you. So I hear a very strong echo. So I'm just wondering if somebody can maybe mute their microphone. 1, 2, 1, 2. Okay. So I'll be talking a little bit about security and reliability of space vehicle communications. So over the years, I have been working on a number of projects. So some of them were on smart manufacturing, some of them were about smart cities, some of them were on smart transport, smart healthcare, and smart grids. And so you can see here some examples of vehicles that would be communicating with each other, or drones, for example, that would be communicating with each other. And the top right corner is showing something about kind of robots on the manufacturing floor and how they can do various things on assembly line. This is the assembly line. So what do all of these networks have in common? Well, all of them have in common the idea of communications. So all of them may have mobile kind of robots or vehicles or drones. And these drones and vehicles or robots need to communicate with each other and maybe have different faults or different disconnections or different latencies. So the idea is, how can these different kind of vehicles be connected into a completely autonomous system that would be functioning on their own and without anything being done by humans. Let's just talk a little bit about the terrestrial internet architectures that we have today. So terrestrial internet, as we know it for the last 40, 50 years, spans wired, wireless, and mobile kind of ad hoc networks. But all of these kinds of networks make strong assumptions about the connectivity. So you see, whether you're talking about cellular networks or wireless networks or even manets or VANETs, we assume that there is availability of end-to-end path. That means that the source and destination can connect to each other. Relatively low RTTs, also very high availability to naming, security services, caching, and searching infrastructures that can, for example, provide locator-based access, such as DNS. So all of these networks, we say, are traditional networks that kind of we as scientists have dealt with very well, and we have made them kind of part of this internet that currently works very well. The question is, what is happening with non-terrestrial architectures or internet architectures? So we say that when connectivity, so end-to-end connectivity, assumptions do not hold, we have the problem that communication is disabled. So we have the problem that any applications would break. And we say that we need fundamentally new communication and security paradigms. And so when we talk about, let's say, small satellite communication or big and small satellite communication, we can clearly see actually that we need to support interoperability among radically heterogeneous networks, and we need to, in a way, provide good performance with very large delays and also unpredictable loss of connectivity. So currently, the networks that are used to kind of support communication between all of these kind of edge nodes, let's call them edge nodes, are DTNs, or delay-tolerant networks. And so these DTNs actually are based on the principle of store, carry, and forward. And they use this principle to transfer the data, and not only data, but security messages as well. So here is something that I'll be talking about or focusing on today. So talking about the routing actually and transferring of data and security messages via this idea of store, carry, and forward principle. So the interplanet satellite communication networks have been envisaged for the last 40 years or so. And so scientists have had this idea of having the internet service in space. So trying to have similar experience in space as what we have here on the ground today. So, okay, that's fine. We can imagine it envisages on the picture to the left here. But what are the characteristics of this kind of internet? If you assume that all of these nodes that are practically mobile here, they have different movement patterns and they communicate with each other. So what are the characteristics of these networks? Well, we can say that characteristics of this kind of internet, if we enable it one day or today, would be for sure high intermittent connectivity. So the actual nodes would not see each other sometimes. They would also not be able to talk to each other, to send data to each other very easily, because the actual propagation delays when they need to talk to each other are extremely long. And we say they're extremely long because, of course, we have a finite speed of light. And of course, when we talk about the radio as well, I think the previous speaker has been giving some specific kind of latency information, how long it would take for a signal to be transferred from Mars to Earth or from any satellite on the moon to Earth. But clearly, these delays are much longer than what we have on Earth. We also have very low transmission reliability, and we also have very low positioning accuracy and limited visibility. So if anyone is interested in this kind of field, you will see many kind of videos, usually done by maybe NASA, but also Berkeley and other kind of academic partners, where they would say, okay, if a particular rover is on the kind of far end of the planet and is trying to kind of communicate with any satellite that is kind of closer to the Earth, for example, well, they can't do it until the planet kind of rotates in such a way so that this rover is positioned kind of along the pathway of communication with the satellites that would be maybe around the Earth or even on Earth. So we say the low transmission reliability, position accuracy are the problem, but also we can also see that we have really very low asymmetric data rates. So when we talk about communication, and if one, let's say, satellite would talk to one satellite in one moment, it does not mean that the satellite that is communicated to will be able to respond to the satellite that send information to it. So we have kind of these characteristics which have been examined by the idea of this interplanetary internet. And we say that DARPA, for example, has been researching it a lot, but also JPL, so this is Jet Propulsion Laboratory, that is kind of part of NASA as well. And because I said that I would be talking about reliability and security, I can say that DTN networks are enabling some reliability of communications in these networks in such a way that they enable communication between different kind of satellites and different edge nodes on one hand, even though we have these characteristics here, but also we can say that the DTNs also provide some kind of security. And I'll be talking about security towards the second part of my talk today, but we can say for now that security is enabled by CCSDS. So CC is, we have these consortiums that have been actually enabled to enable space data systems, and they have been active for many decades until now. And basically what they do is they kind of can propose some protocols, and they can even maybe standardize some protocols. So in this case, in terms of security, CCSDS have kind of proposed the space end-to-end security and space end-to-end reliability. And that was happening over multiple decades. But more recently, we can see that CCSDS is proposing something more kind of interesting, which is multi-hop DTN routing protocol that would be carrying the data and the security messages. So until now, for the majority of time, we didn't have this kind of multi-hop protocol. We were relying maybe on a single hop protocol or maybe even direct communication protocols. But with the emergence of many slides, and especially this small kind of satellite networks, we have this idea of multi-hop DTN routing protocols that are emerging and becoming more interesting. The interplanetary ideas and the DTNs that are supporting interplanetary communications are very closely aligned with actually military battlefield communication networks as well. So it has been multiple decades that as scientists we envisaged that, when we talk about, so these are military battlefields, just one scene where different airplanes, let's say, are communicating with each other. They have to communicate important messages. Well, they do not have consistent network infrastructure. And we can see that and envisage that they can have frequent disruptions, which means that because they are in military, any of them can be distracted at any point of time. So we say the characteristics of military battlefield communication would be high intermittent connectivity. So connections that would be enabled and disabled. We would have mobile distraction that would be happening. We would have a lot of noise, a lot of attacks, a lot of interferences. I believe that there were some questions for the previous talks where people were interested to learn more about this. But in military battlefield, actually, this would be a very standard kind of way of disabling the communication between the edge nodes. And we say that because of this, we have low transmission reliability, low position inaccuracy, limited visibility, very low data rates. So together, these characteristics kind of sound similar to the previous characteristics, satellite characteristics, but still we would say, okay, we have some mobility here, we have some distractions here, but still mobility here would be much smaller than or lower than the mobility for satellite networks. And of course, these attacks that would be happening here in this scenario would be similar to any other kind of attacks that would be happening in the space environment. The differences would be that the delays that we have in the space and in the military battlefield would be orders of magnitude. So we have much larger delays in the space versus military battlefield. We can say that DARPA has been funding a lot of research via DTN projects, so how to support basically communication in the military battlefield. And usually over decades, we have had this managed security that has been used. Managed security meaning mobile ad hoc or vehicle ad hoc network security. So primarily here we assume with managed security that the distances are smaller, delays are smaller. Yes, everything what we said about characteristics is true, but still the scale is smaller compared to the previous context. And we say that for managed security, usually we would have distribution of CAs, certificate authorities, that would provide some kind of security in kind of these scenarios. But then these kind of security approaches would not work, and I'll explain later on why in the context of the space. So let's just talk a little bit about the solar system internet idea. So the communication from Earth to any spacecraft is a complex challenge for many reasons. And here I'll be talking mainly about the extreme distances that we have. So NASA, for example, has been managing 3 different types of communication networks for many decades. And we say, okay, so these kind of networks that are very close to Earth, which are near Earth networks or NENs, for example, they would be significantly less challenging than these space networks, for example, or in general space networks that can comprise all of this. So we can say that NASA for a couple of decades has been supporting the communication between distributed ground stations and then space relay satellites for communicating various data and, of course, receiving various data. So in this sense, we don't see anything particularly new. But what is new is that over the last couple of decades, there has been exactly a dramatic increase of research and deployment of much smaller satellite systems compared to the GEO, MEO, and LEO satellites, right? That we have had for a long time, for multiple decades. So these smaller satellites, we very often can refer to them as satlets, for example. They would weigh, for example, less than 1,000 kilograms, so less than a ton, compared to the GEO, MEO, LEO, they would be much kind of more expensive and much kind of heavier. But in addition to the small satellites, we also have microsatellites that only weigh 10 to 100 kilograms, and also nanosatellites that are from 1 to 10 kilograms, and picosatellites that are, from even less than 1 kilogram. So when you look at these kind of different types of satellites, you can imagine in a way how simple it can be for different companies to launch different picosatellites, nanosatellites, and microsatellites to space and make them do something what they need for their own applications. So the question here is, if we imagine many thousands of small satellites and nanosatellites and picosatellites and microsatellites in space out there, the question becomes really big about how communication happens between these satellites. So we know for now that these satellites require much more communication, much more complex communication needs. And why do they need that? Well, they need it in order to transfer data between these different nodes. And in order to do that, they need to use multi-hop relay communication that goes significantly beyond the point-to-point direct or a single relay link communication, which we had over the beginning of the envisaged kind of satellite networks. The mega constellations are becoming very clear in terms of the small satellites today. As we also heard in the previous talk, most of these small satellites and picosatellites and microsatellites that are launched in space are coming actually maybe from the companies. And these companies are kind of launching these satellites for particular purposes. And these purposes are very often, well, to observe the Earth and to do some kind of remote sensing. And because of that, we can say, okay, there are satellites that are there just to help, for example, agriculture applications or disaster management application, or maybe forestry or wildlife application. More and more, we see also the application for the oceans, so oceanography, because the satellites can actually provide very, very important kind of pictures, 3D pictures that would kind of really help in studying the depth of the oceans. As we know, if you read a little bit about that area, we know very little about the ocean today, maybe even below 10% of ocean, maybe 3 to 9% of the ocean. And so yes, we have some kind of autonomous robots that can be deployed in order to go further down in the ocean, but we really need the satellites so that we can get bigger pictures and to kind of work together with the smart kind of vehicles that are also deployed in the ocean. So oceanography is a big one particular application of satellites. But I would like to point out that in addition, and maybe more importantly, at least for me, compared to these particular applications, we need this mega constellation of satellites, which are pico and nano satellites, in order to treat them as something that's called machine-to-machine communication. So we know that on the ground we have, with 5G and 6G, we have machine-to-machine communications. So why wouldn't we treat satellites as machines that have to be fully automated? So we cannot imagine any kind of person that will be going and fixing something that doesn't work. So everything needs to be remotely operating and working completely autonomously. So that's why we are looking at how can we envisage the use of these satellites beyond what they are originally being kind of envisaged to do, which is only single applications. So let's kind of move on to see them as machine-to-machine communications, and kind of let's see if we can kind of envisage this distributed system, so of routers, if you wish, that would be the system of distributed interconnected satellites that would be supporting and acting actually as the space internet, meaning the routers in the space internet. And as such, they would be able to support any different applications. So we don't want to have one company launching some satellites to support only agriculture application for some time, and then when they don't want to use it anymore, okay, removing the satellites or not, or disaster management. We don't want to do that. We want to repurpose the satellites in such a way they can then be even reprogrammed to do something else. And then all the times that the satellites are going to work as practically very, very smart machines, very smart routers that would be enabling the communication and any other kind of new applications that can come in 10 years or more. So the mega constellation of smart satellites are supported and enabled by DTNs. So we know that the concept of delay tolerant networks is kind of key for enabling communication between satellites. But in addition to that, I'm just going to give you a little bit of a clue here that the term DTN has been introduced by a team of researchers led by Windsurf in 2003. And actually, they started working on it even in 1998, I think. So maybe a little bit more, 4 or 5 years before this time. The idea is the DTNs are important because the communication between satellites cannot be enabled by TCP/IP protocol. And if anyone knows the beginning of the internet, Windsurf has been there to actually exactly propose TCP/IP protocol stack, right? At the beginning of the internet. That's why he's seen as a father of the internet, terrestrial internet. Well, he has also envisaged that why should we stop and support the internet only on Earth? Let's support, by similar principles, the internet, but in space. So what's different between the internet in space and internet on Earth? Well, internet on Earth primarily has these routers that are static, so they're not moving. And that means that the IPs and everything what we know and the other kind of systems that are operating on the top of internet are not changing very much. Well, if we look at the space internet, we can imagine that satellites are actually the routers, and as such, they would be always mobile. So as such, the mobility of the routers, the mobility of this internet is the key. And that mobility has a specific features. And these specific features are that the networks, we say, are changing in time. So we say temporal networks or time evolving networks are connecting the routers. And also, we say that the connectivity between these routers can come and go. So we say that the DTNs in space are, in a way, some kind of time-evolving networks that lack continuous and instantaneous end-to-end connectivity. So that's fine, and every satellite speaks DTN. Currently, it is deployed in space. But more recently, JPL and Scott Burley has identified that actually exactly for this time evolving and partitioned nature of DTNs that are relevant for space, the best kind of idea to approach it, to kind of carry the data, to route the data, is by means of something that's called contacts. So the contacts are so I'll define it in the next slide a little bit more formally, but we can say that the routing that happens in the space internet can follow many kind of principles, but by JPL and Scott Burley, it is exactly the contact graph routing that is particularly important and powerful and can actually help when routing all the messages in the space. So why is this contact graph routing important? Well, contact graph routing can be envisaged as a relatively simple kind of routing compared to many other kind of very AI-driven routing mechanisms, but also because as I will say, that the space does not allow us actually a lot of time to learn and to exchange information, because satellites are moving with extremely high speeds, and when they pass next to each other, it's actually a very, very small amount of time that they have to exchange the information. So this contact routing protocol means really, let us kind of think how the satellites can communicate as efficiently as possible, even though we know that the connectivity is actually very sparse and very, very limited among the satellites. So the JPL and Scott Burley has kind of proposed that, yes, CGR will be using a set of non-trivial algorithms adaptations. And also it needs to also know the space operation concept. So we need to know where the satellites are moving, what their jobs are. Are they going to go make some pictures, then come back? Are they going to go to the International Space Stations and then from there move on? Where are they going to go? So we need need actually to know a little bit about space operation concepts, and we also need to know the time dynamic scheduling, because if we know where the satellites are going, when they are launched, whom they are going to meet, we can actually design really specific complex graphs that are temporal graphs, and we can use them for scheduling the messages or scheduling the routing messages, to be precise here. So this is all about CGR framework that has been really studied a lot over the last several years. And we say that even now there is a lot of research going on in various CGRs, and also lots of development as well, because all of that has to be developed, implemented, and also standardized. So we can see that there is a very huge effort into how the CGRs can be standardized, before they can be deployed on different satellites. A little bit of a high level overview of the term contacts. So contact really is just time during which one node is able to transfer data to another node. So the data, so in this case satellite, is able to transfer the data or receive the data from another node only when they're within range of each other. So when they can see each other and when they can communicate with each other. So this is this contact. And this contact can be measured in terms of seconds, milliseconds, minutes, or more, but usually it's less. So the term contact is not invented only because of the space kind of networks, but rather Windsurf has classified contacts to three big types of contacts. Well, first of all, it was the opportunistic contacts. So in here, one kind of node would have no assumption about the future node that it might meet. So we say opportunistic contacts assume no knowledge of the network at all. And so that's okay, that's opportunistic. Then we also have another kind of type of contact, which is probabilistic contact. Well, in this case, the contact patterns may be inferred from the contact history. So, okay, so that's another type. And then also, more recently, we understood, but there is something that's called actually a schedule contact. This schedule contact refers to the contacts that can be accurately predicted and documented. And if individual nodes can predict the future contacts, we can say, well, they can devise something that is called contact plan. If you wish to compare it to something that we have on the ground, you can imagine trucks, for example, and delivery. So the trucks need to get some goods from one place, one factory, and then deliver it to place A, B, C, and D at exactly certain times, and they use the certain paths, meaning roads. So yes, on Earth we can envisage schedule contacts as well, but it's interesting that in space we kind of tried all of these different contacts in order to disseminate the information, because we didn't know whether scheduling contacts would be precise enough, accurate enough, whether even we can do that. And we tried the previous two as well. Well, as you will see, the scheduling contacts won, and we showed that the pathways that would actually be done via scheduling the path completely would be actually more powerful than the other two kind of types of contacts and the other two types of routing. So let's talk a little bit more about the contact graph routing for space-based networks. The space-based networks, we can say, are inherently sparse networks. That means they're not dense networks. So these satellites sometimes, occasionally, come within the reach of each other. They see each other, they can talk, they can communicate with each other. But also there is another thing, and it is that they are actually constrained resources. So very often when we compare a satellite compared to a mobile phone, we think, okay, satellite can do so many things, it can just store so many things, it can do so many pictures, etc., etc. And we would think that's, just the fact that we are talking about space kind of vehicles that are very powerful. Well, when we actually think about it in more detail and what they are doing and how they're communicating, we can say it is not really so in terms of communication. And communication is really, really, in a way, disabled. And it's disabled exactly because of sparseness and also about limited resources. So these two parts, the sparseness of topology and kind of constrained resources, result in one thing, and it is that all the algorithms that we are kind of designing for communication between the satellites actually need to maximize their performance, but be very resource efficient. Resource efficient resources, yes, storage, because the satellites do not have infinite storage, but also this kind of bandwidth that they see when they pass each other. Okay, so resource has to be kind of used very efficiently, and that means that this a priori knowledge really can help. Because if the satellites know something in advance, they should really use it. They shouldn't use the time when they meet each other to negotiate a lot of stuff, to calculate a lot of stuff. So they need to be very, very, very fast and accurate. So we say that this a priori knowledge can be used to the advantage of scheduling and routing. And as such, we say, okay, the trajectories and orbits of spacecrafts, in a way, can, because they are predetermined, they can help with communication opportunities, and then they can make more predictable routing. And as such, we can see very recently, I think in 2019, in the latest internet drafts proposed for CGR, so this is the contact graph routing, Dijkstra's shortest path actually algorithm was successfully implemented and tested in NASA interplanetary overlay networks, or IONS. So you can read a little bit or listen to Scott Burnley in JPL a lot about it. So in more detail here, I don't have a lot of time to talk about this, but you can, of course, hear a lot about it as well in more detail, because there are courses that are offered for example, students from space that are really focusing on the space engineering, but also physics, of course. We know that CGR has been able for now to demonstrate sufficient accuracy and efficiency, and it has now become a de facto routing framework for space DTNs. And actually the Blue Book that is released by CCSDS has recommended CGR in 2019 as the de facto routing procedure for solar system internet. In networking community, and I come from it, we don't arrive to the solution at once. We actually have to study multiple possible solutions. So I mentioned that CGR has been shown to be the only routing algorithm that can be congruent with the planning and routing and forwarding procedures of scheduled space flight communications and deployments. And so all deployments in DTN currently for space flight missions are adopting CGR. But we haven't come up with that straight away. We have actually been working with epidemic and spread and wait, for example, protocols. Epidemic and spread and wait protocols were kind of possible to use when the space internet was small. So when we didn't have so many, in a way, satellites, or even when the satellites were huge, so NEO, LEO, and MEO, right? But now, when we have many satellites that are maybe smaller satellites, this idea of epidemic and spread and wait protocols would really not work well, because they assumed abundant both link capacity and storage capacity, you see. And then when we actually run these two protocols on the current kind of internet in the simulators, of course, we would see that we get congestion. We get congestion and we cannot support communication and this kind of data dissemination between the nodes. And then we, as a quick fix, we were saying, okay, let us, from this kind of epidemic kind of protocols, move to some more intelligent protocols, which are max prop and profit protocols, and maybe they could help. So we thought, okay, they should be able to help, because maybe they can allow us to infer probability of connectivity by means of metadata that is exchanged between the nodes, between the satellites when they contact each other each time. So each satellite says which other satellites it has met and when. So it's a kind of this connectivity log, very short kind of summary vector. And we thought, okay, it's not a problem for satellites to exchange that. Well, and then, based on this kind of connectivity patterns, predict what's going to happen next. So that's why probabilistic solutions and Max Prop and actually Profit are very good at it. Well, the problem is that didn't really work well, or actually not at all, because the Max Prop and Profit were trying to predict their buffers. So imagine the storage and buffer for every satellite based on these connectivity patterns. So they were trying to kind of rank kind of data internally in terms of whom they will meet next, in a sense. So the idea was, can it work? No, it cannot work very well, because the delays that the satellites had in this kind of, let's say, buffer management or space management that they had on their own, compared to the connectivity delays that it was having, are very, very huge. So simply the kind of buffer delays and kind of connectivity delays could not match at all, and we understood that these protocols would just not be effective. We just could not, they would not perform as they perform on the ground. Okay, so now that we have established that satellites need to use this DTN kind of networks in order to communicate with each other, let's see what's happening with security. So DTN, so these are delay tolerant networks, and so space DTNs, okay, they have really, really big security challenges. And one thing that we can say is, as you can imagine, there is no trusted infrastructure currently in the space, right? So if there is no current trusted infrastructure established there, we cannot use many things that we can use on Earth, such as standard AAA or CIA mechanisms. And also, we do not have density, in a way, enough of the satellites, trusted satellites, so that we can use fully distributed security algorithms that normally we would use for managed and VANET security. So what does this mean? Well, this means that space DTN is really generating a very new class of networks and applications, and we see that the challenges facing the network security community for supporting such applications and networks are really fundamentally profound. So why is it fundamentally profound? Because traditional security approaches that have helped us a lot for wired, wireless, ad hoc kind of mobile networks as well, all of them assume the fully connected paths between all endpoints that wish to communicate, and they've assumed that that path must exist in order for trust kind of building to be possible. Well, now we cannot assume that. So we assume these end-to-end points, yes, they wish to communicate, but the pathways between them they're not there, and still they need to communicate. So how can they communicate, and in a secure manner? So let's look at it a little bit in more detail. How do space DTNs constrain available, let's say, trust building mechanisms? So first of all, the high round trip times in these connections. Well, what do? They do not allow frequent distribution of large number of, let's say, certificate or encryption keys end to end. So when we say end-to-end, we make big difference between end-to-end and hop by hop here. Okay, so you'll see it in a couple of slides, what we mean by that, but we just don't have that, it's not possible. And then the second one, delays and lost connectivity to a key or certificate server. Let's assume that there is one that is like International Space Station, let's say, it can issue some keys, it is trusted. Well, the problem here is the multiple certificate authorities and key servers might be desirable as we move away from these international space stations, for example, but they're not sufficient. And they're not sufficient because of these large delays and loss of connectivities. Because you see this, for example, certificate revocation that normally would work if we don't have these huge delays, or if we don't have so predictable delays, right? So here, when we do have it, we cannot actually, we actually don't have it, because we would not be able to say, okay, we don't trust a particular satellite, it's now in our certificate revocation list, so don't trust it. We would not be able to disseminate it to all the satellites, so that the satellites will be able to act on it. And so So that's just to certificate server. But then the long delays in general. So you see these messages that are being sent, let's say the satellites have messages that they want to send, they can be valid for days or weeks. And so the message expiration kind of dates may depend on should depend on the read of the network, on the dynamics on the network. And so if, for example, validity of some messages, let's say even this revocation kind of information about some satellites or the data, if that at all does not is not even in the same on the same level as the dynamics of the network, then we say that the messages cannot be really efficiently propagated, and these expiration times are not going to even a little bit resemble the types of the network. So these long delays can be really, really critical and really bad. And on the top of all of this, we have constrained bandwidth, as we said. The time that satellites see each other in order to disseminate information between each other is actually very little. And therefore, we have to be very efficient in terms of what information we are exchanging between the satellites. So as we know, if we want to be security aware, we want to have more and more information. So we want to put this information maybe in some kind of header bits, but then at the same time, we want actually to have smaller header bits, and we have to have smaller messages, when we disseminate messages. So how does that work? Well, it's difficult. We are researching it. Let's see if we could have learned something about mobile ad hoc security proposals. So mobile ad hoc networks were smaller scale, and they had smaller delays. That's the first thing. But they did have disruptions, and they did have this difference in delays as well. So how did MANET solve security? Well, usually they were relying on something that's called virtual certificate authority. So if we don't have one certificate authority, let's see if this threshold cryptography can help. And usually in MANETs, yes, it would be able to help, because we would have multiple nodes that are in the same team and fighting another node that are on a different team. So, it wouldn't be isolation of nodes so much as we would have in the space networks. But for the space networks, this would really not be applicable, because we don't have the existence of these third trusted parties. And also we thought, okay, can we do the BGP, so certificate chaining, if we assume, okay, let's try to use this BGP kind of paradigm? Well, again, it would not be useful. So BGP assumes that if, for example, one trusted node has signed a certificate for some node, and then that node then automatically is trusted, so that node can sign another certificate, and so on and so on. So we call it a certificate graph. Well, maybe for MANET, yes, we would have actually a certificate graph that would be dynamic, but it would be there. It wouldn't be a sparse network. Well, here for the space, we actually, because of the sparseness, we have insufficient density of the certificate graphs. So actually, we have a problem. So we cannot use that either. And in general, node-to-node key management based on mobility. So we had that in the internet, peer-to-peer communication, especially for multimedia. That would be not applicable because of exactly the certificate revocation mechanism. That would not be able to be kind of sent to all the nodes. So the nodes have to communicate and receive that message in timely manner. So eliminating all forms, we say, on online and also offline TTPs. These are third trusted parties. Offline TTPs refer to this kind of virtual certificates or this kind of certificate graphs. So this is when we don't have access to the one third trusted party. So yes, eliminating all forms of this is a problem. So we say now, we think as a community that maybe if we could combine some self-organized approaches with an offline TTP, maybe that could help actually to achieve some adequate security with the space networks. So what do space DTNs currently have? So space DTN security goals really have only this kind of 6 things here, and this is in line with DTNs. So DTNs and in line with DTNs, space DTNs are focusing on protecting the infrastructure itself. What does it mean? So the DTNs and space DTNs assume they have low resources. They have a problem with that. So what can they do? They need to primarily protect the infrastructure. First, the infrastructure, so these kind of router nodes. So how are they going to do that? Well, by preventing access by unauthorized applications, that's the first thing. Then preventing unauthorized applications from asserting control over DTN infrastructure. Then the third thing is prevent authorized applications from sending bundles. Bundle is a message, but this is a DTN term of a message. So this bundle only means the DTN message. So prevent authorized applications from sending bundles at a rate or class for which they lack permission. So that's another thing. And another thing, promptly detect and discard bundles that were not sent by authorized users. The fifth one is promptly detect and discard bundles whose headers have been modified. And finally, promptly detect and disable compromised entities. All of this here is meant to simply protect the infrastructure itself. All of this is something that we say mandatory applications. And then completely non-mandatory, we say secondary emphasis of DTN is on providing optional end-to-end security for various applications. That means that DTN networks are really trying to really protect, let's say, the satellite, and that satellite forwarding and receiving certain kind of bundles in this case, and not so much worrying about particular picture that has been taken by a camera, maybe that was deployed by a certain company or another company or third company. So they don't care about this data. So existing space DTN security is really the bundle protocol, and it is hop by hop. What does it mean, hop by hop? Well, we said that for us, the satellites are practically mobile routers, and they receive these bundles. They can check the header integrity. They can also check the hop by hop bundle sender authentication. I'll just show it in the next couple of slides. And they do not worry about end-to-end security. That will be clear a little bit in a couple of slides. So we also say that the mandatory space DTN is supporting access control so that only legitimate kind of applications and users with appropriate permission may inject bundles to the network. And also, because of this hop by hop security, it kind of does manage some limited protection against DOS for detecting illegitimate traffic, because in a way, if something gets detected inside the network, so within the first hop, for example, we do in a way protect the source and the destination, so end-to-end communication. So we can say we do that even though it is not the particular mandatory aim for the DTN security. But okay, more and more as we have the small satellites and more kind of applications that are being launched kind of on daily basis to the space, and these daily this kind of small satellites and kind of different companies, they really care mainly about their own application data. So they even underestimate the security of the satellites, but they want to get the application of their pictures or anything else that they're monitoring. So, so what's happening here? We really want to see, can this optional space end-to-end security improve? So the optional end security is end-to-end bundle integrity. So what can we do to make sure that nothing has happened to the bundle that has been sent from a particular satellite all the way to the ground, let's say? Or end-to-end bundle source and destination authentication. Can we make sure that the actual data that has been sent by a particular source, let's say source here is a satellite, and the destination, so it's then edge, the final edge destination is a particular company on Earth, or it can be vice versa. Can we make sure that this authentication from source to destination is there? well, we more and more care about that, and we also care about this replay detection at the destination, and we really want to more and more support end-to-end payload confidentiality, because the different companies really would not want to steal the data from each other, right, and to spy on the data from each other, etc. So, okay, so we can see that more and more, for the reasons of different kind of companies, there is attention to this kind of payload security. And we can say, okay, we can support that. And we say that the capabilities for supporting this kind of end-to-end security are there to kind of enforce a finer granularity access control. Because you see, the primary access control is already handled by the DTN architecture, by the routing, by the actual individual kind of routing nodes inside the network, deep in the network. This is the space network. But okay, yes, we now want to do more than only that. So this is a simple overview of DTN security, and I usually use it just to kind of show the differences between what we mean end-to-end. So end-to-end is source and the destination. You can imagine this as a ground station, and this is a satellite that a particular company has deployed, or vice versa. So the communication that is end-to-end communication. So one is source, one is destination. But their communication happens along multiple hops, and these hops here, so you see, are, the source and destination refers to this source and this destination, but all multiple hops that are along the way for enabling their communication are called senders and receivers. So every router that receives some data and has to forward it on is called the sender, and every other router, okay, satellite, a vehicle, whatever, that receives it, it's called receiver. So not destination, receiver. So we have receivers, senders and receivers that are inside the network, and source and destination is only kept for the kind of two edges that have sent or receiving the data. So here you can see very briefly the difference. For example, payload security header. So it comes from the source to the destination. So this is this PSH. Just look at it here. Is very different from bundle authentication header. Look at this. Bundle authentication headers are some kind of headers that are encrypted. Well, that are encrypted. Yes, they're all encrypted. So we all have encryption here, which is one encryption. I'll mention that later on. AES, you can imagine. But here, the payload security header is computed once at the source bundle agent. Then it is carried by multiple hops unchanged, and it is checked at the destination. So here is the destination bundle agent, and basically the destination needs to make sure that nothing bad has happened with it. But on the other hand, every intermediary node here is checking bundle authentication header, and this bundle authentication header is computed once with every time the sending bundle is being sent, and it is checked each time it is being received in individual hops. So you can see what is happening inside the network and then kind of on the edge of the networks. So it is similar to what we have with the current traditional internet, because we have the layering of the network, right? So we have kind of the routing, the forwarding, and the application data. So this is the application here, what you see, and this here is routing and forwarding. So just to kind of bring it closer to you. So yes, so this is what DTNs kind of support. So what are the current issues and efforts? So the current Space DTN security initiative is based on a pre-shared secret. So it is all based on AES. So this is basically a symmetric cryptography, maybe very, very good cryptography, but still symmetric cryptography. So we say it is still made based on pre-shared secret. And it does not involve any trust dynamics. So what does this mean? This means that space DTN nodes would work very well, let's say, against external threats. So let's say if we use AES, well, we can't break it very easily on one hand. But on the other hand, what happens if some of the existing nodes become compromised. So what happens then? So we say that any symmetric cryptography, especially when it's very good, it has good algorithms and everything, well, it works very good against external threats, but it is really not applicable against internal threats. So what are the internal threats? Internal threats are threats which are supposed to kick off when we have a mechanism that exists that can reevaluate nodes' credentials, you see, and we don't have that. We don't have that currently, and we say that if a trusted node would get compromised, we would start doing something, but it is not supposed to be doing, we cannot detect that. So most recent efforts in the space DTN community are moving towards kind of extending this DTN security bundle protocol, which we overviewed over the previous couple of slides, with novel, dynamic, and we can say fluid trust building and propagation mechanisms. So how are we going to do that? We're going to do it by merging DTN paradigms with other paradigms to allow them to kind of base its decision on behavioral monitoring and anomalous behavior detection, and also detect kind of understanding these connections. Are they predicted? Are they not? And enabling some non-consensus asynchronous partial trust claiming. So what does this mean? Since these networks are disconnected, we can envisage that some parts of the networks would have some satellites that would have some companies working there, and they would trust each other. But then the other and disconnected part of the big kind of satellite space internet would have different kind of companies and satellites that also trust each other, but between each other they would not trust each other. So what happens when they come across each other and they can communicate with each other? So do they trust each other or do they not? So how does that happen? So you see, we were talking about this non-consensus asynchronous partial trust claiming is very important. So yes, some things can be trusted, but the other things would not be trusted. So when we look at these efforts, we can say that they're closely envisaged with the current goals of IETFs and also DTN research group and DARPA and many other kind of companies. And all of that you can read more. I think it's not secret. I mean, you can read it. But yes, we are moving towards this kind of new efforts. It's very interesting to mention exactly because for many years, DTNs and kind of have been helping the space networks, and they have been helping by supporting kind of this infrastructure only communication, so supporting the DTN infrastructure itself. So more and more, we are interested in supporting the data or the payload and security for that. So how are we going to do that? Well, the DTN will not change. It's supporting whatever it's supporting in the previous slides. But if we envisage that DTN routing can start utilizing information-centric networks paradigms, so ICN paradigms, these are the paradigms that worry only about the payload. So they don't care about the rest of the networks and the publishers and subscribers and who is interested in what and what the data is about. They only care about this content awareness. So what does this mean? They need to, in a way, help us protect the data, irrespectively of the network. So how does that work? Well, we are actually starting to see integration of DTN with ICNs, and the ICNs are there helping DTNs in order to allow it to cache the signed content inside the big, potentially, space networks. So what does this mean? If we look at DTN and ICN merged together, we are going to have both disruption tolerance and this delay tolerance because of the store, carry, and forward principle, and also because of ICNs that has this global caching of signed content. We have the kind of trusted by default information or content retrieval and awareness. So how does DTN and ICN kind of work? DTN, ICN kind of based architectures are built on asynchronous publish-subscribe paradigms. So until now, we were talking about senders and receivers or sources and destinations. Well, now, in order to merge with the ICN paradigm, we're talking about publishers and subscribers. So publishers are the nodes that are publishing some content. It could be images of the ocean, images of the fires, whatever it is. And then subscribers are all the nodes that are interested in it. They might be interested because they want to process, do something with it, or they want to just forward it to the other node. So, publish, subscribe is very kind of diverse kind of principle here. So we say all kind of users that subscribe to some content, they will actually get that content. So they will get it via DTN paradigms. So it's kind of, these two kind of paradigms are really helping each other and are very congruent with each other, because neither ICN requires the publishers and subscribers of any content to kind of hear from each other. They might never even meet each other. They might never pass next to each other. They might not even have a contact, even for a 1 millisecond between each other, but they will be connected via multiple DTN hops. So that's fine for both ICNs, and of course DTN is happy to do that. So we say the DTN ICN network contents are explicitly mapped to some object names. Object name is a data name, and it can enable more advanced content-aware routing and security. So basically, if we talk about the content only, the content doesn't care about the network, but it cares about itself, about its own identifiers. These identifiers can be anything, anything that means something to that company or to that application that is, taking photos, images, or any other kind of things. So it's a very big space of naming. You can read about ICN and CCN and other kind of naming that can work here. They're different from DTN naming. They're really just about the content naming. And the idea is that all the contents that get kind of put on the network and get kind of disseminated across the network, cached across the network, it has to be signed, which means we get additional level of security that is this time content security, which has not been enabled with DTN kind of networks. So we say that these ICN networks implement distributed caching functionalities throughout the whole DTN network, and hopefully when we mix DTNs and ICNs, we get kind of protection of both the network itself, so the DTN network itself, the satellite network itself, but also the contents that the satellites have. This is a small kind of overview of what you can imagine is happening with the space DTN and ICN future security initiatives. So if you look at the self-organized DTN security, we will have the DTN and ICN security parts. So that's fine. So we have message integrity, sender authentication, access control. We have the data as well, sign up and everything that comes with ICN. So that's one thing. But the other thing is, so we need to have something like reputation. So reputation is when the kind of nodes, whatever the nodes are, rovers, satellites, space stations, whatever, they will have different information on what they see, and they will be able to compare what they see compared to their, let's say, contact plans, what they know about the network, and compare it with what the particular nodes are telling it. So the important thing is here, every node should be able to, in a way, compare and spot differences. And when there are differences in terms of anything that the node kind of sees for itself, so these kind of first observations from other nodes, what it hears from other nodes, and what it knows itself about the nodes. If there are discrepancies, well, then we know that something has happened, and the particular trust level of a particular node, because this is all working in a distributed manner. So that's why this reputation system has to kind of work continuously. We can say, okay, we do not trust some nodes, and we can say that the direct reputation via indirect reputation has been resolved in such a way that that satellite particularly, or maybe this particular data from that particular satellite, but maybe some other data from that particular satellite would be fine, but maybe just that data from that satellite will not be fine, will not be trusted because it doesn't match the rest. And of course, everything else in terms of the movement patterns, if the connectivities that we hear and that we see from the nodes does not match the contact plans that we have about the nodes and the nodes that have about themselves and about the nodes, if there are discrepancies about that, well, we can say, okay, there is something wrong and we cannot trust either the data or even that particular satellite. Because here you can see that we can observe the nodes both in terms of the mobility methods of the nodes, but also what these nodes are reporting, so what they're telling us. So we are having multi-layer observation between the nodes. So in terms of conclusions, we can say really, despite a great deal of emerging research dealing with security of mobile ad hoc, DTN, and ICN networks, supporting secure routing in environment with little or no infrastructure remains a difficult and fundamentally profound problem. So why is that so? Well, because the current decentralized, self-organized, ad hoc security approaches do not integrate support for disconnections. So we have had peer-to-peer systems for many years. We have had mobile ad hoc networks for many years, but they do not support the DTN part. Okay, so you see, they do not. So we cannot reuse something which was maybe helping us in the past. But also the security approaches for disconnection tolerant networks or delay tolerant networks, they actually do not support dynamics and self-organization. So as you can see, these two worlds kind of have not been talking to each other. They have, we do not have something that would be able to merge all of this. So we say as space DTNs get more widely deployed, so by many companies, by many governments, it becomes really increasingly important to get more commercial and government efforts kind of in line and directed towards extending current space DTN security to allow this dynamic, smart, intelligent trust management. So this is where we are. And yeah, I'm very happy to answer any of your questions. Thank you very much for your attention. All questions are welcome. I will just bring myself back to the beginning of the title of this. And yes, I'm now just waiting for your questions.
Yes, any questions from the audience, online, offline side?
I'm a bit. I can't hear you. I can't hear anything.
Yeah, Dr. Milena, we came to know about your funded projects. Then we came to know about your terrestrial and non-terrestrial internet architecture. Then we came to know about internet, planet, satellite communication, especially the internet service in the space. We come to know about your solar system internet. During your presentation, we came to know about mega constellation of the smaller satellites. You have very well explained about the contact graph routing, CGR, for space-based network. You have very well explained about the space DTN security challenges and its mechanism. You also explained about the space DTN security current issues and efforts. So there are many things we come to know about your presentation and details about it. So this time, due to the pandemic situation, we are not able to greet you in the presence. Hope so soon we will be able to in presence you and will let you know more about you and your research. So thank you, Milena, about your presentation. As a token of appreciation, I request my colleague to give you one certificate for your presentation. Thank you, Milena.
Thank you very much. It was a pleasure to see you and to be able to give this talk. Thank you. Thank you.
Thank you, ma'am, for your kind presence, ma'am. Have a good
Thank
day.
you very much. It was very nice. I'm very happy to answer any questions. There.
I think there is no questions, ma'am. Still, if any student have any question, we'll surely contact you through email.
Thank you so much. Yes, they have my email. Thank you so much.
Thank you. Thank you. Have a good day, ma'am.
Yes, thank you. Bye bye.
Yeah, thank you. Thank you, ma'am. Dr. Surendra Sunda, sir, are you here? Surendra, sir?
Yes, go ahead.
Sir, if you wish to check your presentation, you can check it today only, sir, through this meeting only, sir.
Okay.
Okay.
ठीक है.
Sir, it is visible. Make it in presentation mode, sir. Yes, sir. It is fine, sir. It's fine, sir. Yes, sir. It's moving, sir.
Okay, graphics are okay.
Sir, any audio is there, sir, in this presentation,
No,
sir? Any audio?
audio only the pictures.
Okay, fine then, sir. Yes, sir. It's fine, sir. I think, sir, the same link you can use tomorrow as per your schedule, sir.
Okay, no problem.
Okay, sir. See you tomorrow, sir.
Yeah, okay. Bye.
Okay. Thank you, sir. Have a good day.
एंड लीव
एंड कर देता हूँ.
एंड करके कल स्टार्ट कर सकते हैं वापस.